All right, so we had started talking about data modeling on Thursday. I think we talked about a little bit about sequence diagrams and whatnot. And I believe you are already familiar with entities and creating classes and doing some data modeling, one-to-many, many-to-many mappings and whatnot. So I'm going to skip over that. So attributes, UML domains, dictionaries, unique identifiers. Okay, so let's talk a little bit more about relationships. So as part of the process of data modeling, we should have gone through the process of identifying nouns, verbs, and the relationships between the different attributes and classes. And so at some point we need to start working on describing a little more what the relationships are between our data set, right? And there are two high-level ways of talking about relationships. One is association and generalization, of which I believe you're already familiar with some of these. Okay. So generalization, I think we talked about it, is being able to implement base classes and subclasses, and is generally implemented by using inheritance in object-oriented technology. Association is a fairly vague term that where we want to be as much as we can formal on capturing what is the relationship of one class with another class, or one object versus another object. We like to capture, for instance, how many in a relationship are participating, right? If if I'm creating a playlist, on iTunes, well, it would be that these would be my own playlists, right? So there would be me, just one of me, and there might be many playlists, right? And then you might be organizing your songs into many of these playlists. So presumably there would be a relationship of a one-to-many relationship between each playlist with many songs. Yes. So certainly we like to be able to capture how many of each instance are participating in a relationship. So associations allows us to capture those kinds of information. Also, it might be that I want to capture relationship between actors and movies, right? And it might be that one actor can act in many movies, but if you give me a particular movie, there might be many different actors. So it seems that there might be a many-to-many relationship, right? Many of instances of actors are related to many instances of movies. So associations allows us to capture these, and these they're captured in UML at a very abstract level, right? They don't talk about. We don't capture here how we create that in a concrete sense, right? This does not capture how we actually implement it in SQL, or how to implement it in Java, or how we implement it in Node.js or JavaScript. It captures a very, very high level. Then mapping this data model to a specific concrete stack, that's another issue, right? On how is it that is mapped. All right, so first let's talk about this high-level representation. So here we have some examples on relationships between portfolios and investors. So one investor might have many portfolios, or in a particular sale, there might be many associates or many sales representatives that participated in a particular sale. Or if you have a student, you might have one single transcript from one institution, but you might have many transcripts from various institutions, right? So we like to identify how many in the relationships are participating, on whether it's a unidirectional, right, or is it bidirectional as well. So typically the work of identifying these relationships and the classes and the attributes, they all start with reading through the interviews, right, and the use cases that we had captured from interviewing our stakeholders, right? There might be lots and lots of different nouns, lots of different verbs, that create the relationship between these various nouns. Now, the specifics of use of working through these skills is mostly the focus of other courses, like well, in graduate school it's 5200. I don't know in undergrad, what is it, 3200? Where you do a lot of data modeling and SQL and whatnot. Yeah. So that course goes into lots of details on that. Here, I'm just going to skim through it a little bit. One of the tasks is identifying, how many participate, how many of one participate. So, for instance, you might say that giving a particular course is only ever one instructor that teaches that particular course. So if you give me an instructor, they only ever teach one course. If you give me one course, only ever is taught by one particular instructor. Or you might have that one instructor can teach anywhere between 1 and 10 courses, so it has a minimum and a maximum. But certainly at least 1, but at most 10. So this cardinality is a notation that just gives us an idea on how many participate in a relationship. Or here we have an unbounded number of courses that an instructor could teach. And if we don't write down the cardinality, then it defaults to 1. Again, this is only to be as formal as possible to convey this and to share this with other engineers. Some of them will be in the database field. Some of them will be on writing the back end. Some folks will be writing the Java side. Some folks will be writing the front end. And as much as you write this in such a way to be normalized, right, and to remove any redundancy in the data model, oftentimes you'll have to denormalize the data structure to be consumed on the client side, oftentimes by creating views that collate data from various tables from different classes into one convenient view for human consumption. But again, those are two aspects of data modeling. Here's a full specification for capturing relationships and associations between two generic classes, where we are labeling the direction in which the relationship that we're capturing. How many are participating on either end of the roles. We are naming the particular role that a high-level role that one of the ends is participating in this relationship, and the cardinality and how many of these. Some constraints, right? Whether this is ordered, that certain values are required, and that have some boundaries and some validation with each one of these constraints. Generalization allows us to capture an organization and reusability of certain entities that have common attributes, right? That we don't want to have to capture this data over and over across different instances. Instead, we try to generalize, right, and create abstract classes that can encapsulate some of the common attributes that are similar across multiple entities. So typically we implement that in object-oriented programming by inheritance, right, where we use extends or implements, depending on your particular stack. So here's one particular one. Depending on how you view it, sometimes referred to as generalization, or sometimes it's referred to as specialization, right? If you look at it from bottom up, then you are generalizing, right? If you're moving up the hierarchy, it's more and more general. If you start from the top and look bottom, you refer to as specialization. You're creating a special case. So employees, students, all these are special cases of a Northeastern person, and faculty and staff are special cases or special types of employees, whereas graduate and undergraduate are special cases of students. There are different notations that basically say exactly the same thing. Now, the other names for the same thing, it's also known as the parent-child relationship, or the supertype, subtype, or abstract, or concrete, or base and derived. It's known by various names, okay? But it's basically the same idea, right? We are capturing some attributes that are in common with everybody, and we are grouping it into a higher level of abstraction. Oftentimes, these abstraction might be too abstract to talk about them in any concrete sense, or to be useful in any way, that we can't represent them, or we can't instantiate them, or we can't, for example, when if we talk about different types of shapes, rectangles and triangles and circles, they all have very concrete representations in a 2D space. But if you're building a drawing tool, it oftentimes is convenient to think about these in a generic sense as shapes, right? And iterate over all the shapes and talk about all the things that are in common of all shapes. They all have an XY position. They all might have the same foreground color. They all might have the same font. But nevertheless, shapes, collecting all these attributes that are in common with all shapes is not concrete enough to actually render it on the screen, right? You might have to go down to a specific type of shape to actually render it on the screen. Now, sometimes we get a little bit too carried away on over-engineering some of these base classes and derived classes and whatnot, and we might consider something to be hierarchical when it's not, right? So, for instance, if you consider students and you might consider freshmen and sophomore and junior and senior, you might consider them to be different types of a student, right? So you might be tempted to have a base class student and then have subclasses as freshman, sophomore, junior, and senior, right? Whereas a better perhaps representation might be that it's actually they don't have anything, there's no difference between them. It's only that they might have different state information for the same instance of a student. Okay, so they're not adding any new information that is unique to a freshman, that is unique to a sophomore, that is unique to a junior, other than a student. Yes, so it might be better be represented as a state variable, right? That what is your current status in the college, right? Whether you're a freshman, sophomore, as opposed to having a subclass representation. Aggregation is just one special case of an association that just adds a little more details on the association. It often is used to represent the fact that one class is made up, instances of one class is make up a bigger portion of another class, right? Where you might say that an order is made up of different products that are in that particular order, or playlist is made up of many songs, and if you want to, or you might say a page contains many widgets, or a website is made up of many pages. So to capture this type of relationship that one is made up of several, right? The whole and the parts. Aggregation is often tries to convey that kind of relationship. But oftentimes just a regular association is plenty. Although aggregations might add just that little more documentation. And there are also different types of aggregation where depending on the life cycle of these classes, where, for instance, if the life cycle of one depends on the life cycle of the other, we might be considering not aggregation but composition. Right? Composition would be rendered, I don't think it's shown here. Yeah, so aggregation is rendered with an open diamond on the parent, saying that the child on the right-hand side the life cycle of the child does not depend on the life cycle of the parent. Okay, meaning that if I remove the parent, I don't necessarily remove the children. So for instance, if I have an order and I remove and you have, for one order, you have many products, right? It might make no sense that if I remove the order, I might also remove the products. That makes no sense, right? Or if I remove a playlist that contains many songs, if I remove the playlist, typically I don't also remove the songs, right? But say I have a data model where I'm capturing a website that contains many pages, yes? Or one page might contain many widgets, yes? If I remove a page, would it make sense to keep track of the widgets? Maybe not. If I remove an entire page, it might make sense to also cascade delete all the widgets that were also in that page. I don't want to keep track of them in the database, yes? So in that case, we might consider that to be a composition, right? Yes? Yeah, it's a business decision, right? So for instance, you might say, what happens to, say I'm in Facebook and what happens to my posts, right? all the content that I generate, and I no longer want to be part of the community, right? And I want Facebook to remove me from their databases. What happens to all the data that was related to me? Should that also be removed? So that typically becomes a business decision on whether you want to keep them around or not, or how much you want to keep it around to maybe share. Do you want to keep a particular widget around to share it in a particular other page? Maybe, right? Or maybe you have a page that can be shared across many websites? Maybe, right? So it depends, right? It's up to you that you decide what the life cycle of parent-child relationship is. And you decide, obviously, it'd be for a particular use case, and you can argue one way or the other. Here you have a car keeping track of many wheels. So one car has 3 to 4 wheels, or maybe 6 wheels, 3 to 6 wheels. Validating data, typically we also add additional constraints on the fields, right? And whether certain things might be required or that have to meet a particular design string, regular expression, and specifically we would like to be able to come back and run this data model with our stakeholders, right? And say, well, give me an instance, give me an example of a particular object or particular class, right? Can you think of an instance, right? And can you think of an instance where one of these objects is related to many other objects, right? And oftentimes we can grab this from the use case analysis, but always running it by the stakeholder, the user responsible for this, right? And also see if we could talk through the data model and find can we translate this back into an English representation of the data model. So presumably we have the use cases. From the use cases we generate a data model, and then can the data model then reconvert it back into English, right? Ideally, right, you would come back with a translation that matches somewhat what you have captured from the original use case, right? Java, this is just runs through several examples of converting various data models into their equivalents in Java. Here we have a one-to-one, where we have one student having one address, so one-to-one relationship, and being captured in two Java classes as student classes and address classes, and one is being referenced to the other. Here's an example, a user interface for navigating between a student and their address. If you click on the address, you navigate maybe to the instance of that address, perhaps in a separate window. When you click on back, you go back to the student. So there's one-to-one. There's one student, one address. Or you can have a many-to-many, where you might have one student and several sections represented either as a set or an array list, or linked list, right? Depending on what data type you want to use to capture the multiplicity. So here we have a student that has multiple sections, and each section might then be related to many courses, right? And you might want to capture that in a user interface where you might have a student where you click on the sections, it lists many sections, and where that particular student is enrolled, and if you then click on any individual section, you can then view that particular section with its name, description, how many folks are in there, whatnot, what grade you got perhaps in that particular section when you enroll there, and then what course is for this particular section, and that might be a many-to-one, right, where you have many sections, associated to this one particular course, right? And if you go back and you navigate, this is a very common user interface design pattern, right, where you start off from a particular data point, in this case a student. You navigate to multiple instances that are related to that one instance, and then you have a kind of like a master-slave user interface where you do a list of all the instances, and then you can select any one of them to view the details of that one particular one. And if we had time, perhaps we could have prototyped this. So the idea would be to convert these data models into a concrete representation in Java. Some of these tools, you can start off from the data model. One of them that I find very useful is a visual paradigm. The full-blown paid-for version can do forward and backwards code generation, right? You can, for instance, press a button and it generates for you the Java classes and the array list and everything stubbed out that you can then go in and fill in the code. Oftentimes, developers don't care much for the code that is generated with these tools, but at least it gives you a place to start. It can also do reverse engineering. You can point it to source code and generate a graphical representation of the data model that makes it much easier to look and interpret what's going on. All right, I'm going to leave it here.